Hi, this is Clay Hearn. I'm also joined with Adrian Jensen is also on the line too, and he will help kind of field any questions that might be coming in during this webinar. In this webinar, we're going to focus on geometry creation in STAR and kind of an angle towards effective practices for setting up your geometry. So first here is kind of an overview of what we look to cover in this webinar. First, kind of a little bit more information about ourselves and kind of the CFD experience that we have with applied CAX. Then we'll kind of dive into the geometry capabilities within STAR-CCM+, look at ways of importing geometry into STAR, and dive a little bit more into creation and manipulation of the geometry in STAR. You can do this with a built-in CAD tool that is in STAR. Also getting familiar with the meshing pipeline. And then we've got about 3 kind of breakout examples to look at, kind of how to deal with some simple geometry where one might only have a surface mesh information that lacks any CAD data, how to bring in a CAD part and do some quick manipulations on that. And then kind of our last item down here is our office room at Applied CAX. It's kind of a quick overview of many of the programs that we've been working on at Applied CAX, and primarily our consulting arm that's called Predictive Engineering. We use STAR every day, so it's not like we're just kind of an application engineer that's kind of looking at making pretty pictures. These are real consulting projects where we're using STAR and trying to get real engineering answers and solutions to them. One here in the top left, that was a rail car that we did the HVAC analysis on. It was full thermal heat transfer. We had electronic loads, electronic cabinets on either end of the vehicle that we also had to consider. Kind of some of our more complex analyses where we take advantage of the multi-phase capabilities in STAR, combustion in a recovery boiler where we're using solid fuel bark and tracking paths and the devolatilization, drying, and combustion. A little bit on the easier end of silt dispersion within pipes. And then also an electronics cabinet that includes conjugate heat transfer, radiation, heat loads from the outside in it. And the thing with all these is all these parts were created within STAR. The geometry was all created in STAR, or at least heavily modified within STAR using the CAD tools that were provided. So just an overview of geometry in STAR. It offers a wide array of methods for importing and manipulating geometry to begin the analysis. This is really the first step to any analysis, and it's somewhat, in my mind, a little bit of an overlooked step. People get kind of focused on applying the boundary conditions, the meshing, the physics, but if you don't have a good geometry to start your analysis off, everything down the road could be compromised. There are powerful tools available within STAR to allow 3D connection, or to allow bidirectional connectivity between the analysis simulation toolkit and the 3D CAD. This allows you to make changes within the 3D CAD and automate rebuilding, remeshing, and rerunning the analysis. So in this webinar, we're going to try to give you a quick introduction to building, importing geometry within STAR. We're going to look at how to handle the surface mesh that may lack any CAD description, and how to manipulate the CAD geometry to defeature and extract the fluid volume. And then lastly, we're going to look at putting all these techniques together in our office room setup, where we can take advantage of the parameterization and the automation of refining and rebuilding the geometry. So there's numerous methods for importing geometry into STAR. Uh, typically, in most applications, you typically have some geometry that was available. Either it might be a CAD model that was developed by a designer, or some other results that may have come out of another analysis, and it may just be a surface mesh that's available. But many times, say 80–90% of the time, there's something available that you can import as your geometry and get going. On the surface mesh front, we have a list of formats that are available for direct import into STAR. With these items, typically it's just a surface mesh. There's no CAD geometry behind it. It can be a little bit more cumbersome to work with, but there are tools within STAR such as the surface mesher or surface wrapper that can be used to re-extract a usable volume for your analysis. And if we move into the CAD formats, there are neutral formats and native CAD formats. Neutral formats such as IGES, STEP, Parasolid ACES, these are all formats that CAD tools such as NX, Solid Edge, SolidWorks, CATIA can all export their native formats out to. So there's always that way of getting geometry into STAR that was developed in a CAD format. If you do want a better linkage to the CAD formats, there are direct tools for directly importing from, say, NX, Inventor, SolidWorks, and CATIA directly into STAR. Typically, they require an add-on license for those functions. And lastly, there's XML formats that we won't really get into much. These are primarily assembly structure components that may contain either CAD or surface data. To start off with in STAR, we do have a full CAD tool. So when we talk about the CAD tool in STAR, it's a fully fledged, feature-based parametric modeling tool. You start off with sketches that can be defined either on a surface or a plane. You can see in here we've got kind of your three basic datum planes. And from these sketches, you create shapes and volumes, either by extrusions, revolving. You can create surfaces. You can also remove material, remove volume by cut commands. And one of the strengths of this being a parametric tool and feature base is that, as with tools like SolidWorks and Solid Edge and X, you can go through, you create a number of list of functions, a list of features that you're using to define your geometry. You can always go back in history, change a sketch, modify a dimension, modify an extrusion somewhere, and it automatically goes back through and rebuilds all the steps that you take. And this is a key feature for going forward. Because with this feature of going forward and having that feature-based tool is now we can open the model up to parameterization. So if we have a sketch here that, say, this is just maybe a length and a width with a radius hole through that, we can open up all these dimensions to be an exposed parameter, such as we expose the whole radius that's shown here. Now that these are design parameters that are open and available, we can always go back through, update that whole radius, update that length, and that will rebuild the geometry and be reflected in our final parts all the way out to assembly. In addition to the CAD handling, there's also meshing operations and the meshing pipeline to be aware of. And this is on the simulation side. So we bring in parts and then we'll create a list of operations that kind of lead up to the mesh. What we have here is kind of an example of a part that we did with our local list of meshing operations. And here we had a couple heaters that we brought in that were originally positioned at an origin point. We had a couple operations defined to reposition where those heaters are in the space of this fan room shown here. And then we create other operations such as subtracting, imprinting, and volume extraction that allows us to get to our final part that we're going to use for building up our solution domain in our mesh. And we'll show you this a little bit more in detail in an upcoming example. But the key part is because we have this list of meshing operations here and this meshing pipeline, that this is all fully repeatable. If we change parameters that drive the location of these heaters, everything gets updated automatically. There's a number of operations available either on prepare, where we surface wrapper, fill holes, extract volumes in order to define our geometry. We have Boolean operations where we could either unite or subtract components together. And then the last part is always the generating a mesh, and that's done once your domain, your regions have been defined. What we do want to start off with on our first example is how to deal with surface geometry when you bring it in. And there's a couple tools to use that's a little bit outside of CAD. The first tool is the Surface Repair Toolkit. And the Surface Repair Toolkit is basically a way of directly repairing the features of a geometry as it's been brought in. This is also a very good toolkit to use even if you're dealing with a CAD geometry. If you've got your part set up, you've gone through, you've done all your meshing pipeline operations, you're ready to mesh, and you get a fault that springs up that says there's a non-manifold edge or there's pierced faces, we can't complete the mesh correctly, you can always bring that part into the Surface Repair Toolkit, whether or not it was originally CAD or a surface geometry, run a diagnostic on it and identify areas where you had pierced faces, free edges, or non-manifold edges that'll prevent you from, or non-manifold edges or non-manifold vertices that'll prevent you from successfully maintaining a mesh. This can either direct you, if it was a CAD part, to maybe go back into the CAD to do some repairs here in order to get a usable geometry, or within the Surface Repair Toolkit, there are tools that go directly to repairing that surface locally. We're not going to get too far into that because that would really require its own webinar. Same with the surface wrapper. This can be used for basically saran wrapping your surface. This is really good tool to use for dealing with items if you have a very complex CAD geometry that has a lot of surface features on it, or if you've got non-CAD geometry that you need to deal with. So in this first example, we do want to get into a little bit of the intricacies of working with a surface mesh file. Surface mesh file, anytime you import a CAD part into the simulation domain for STAR, it always does come in as a surface mesh. Now, if its basis is a CAD part, it does still retain the CAD model descriptions. And those CAD model descriptions could be items relating to the surface. Say if you have a radius, it understands that this is a radius, that it has a certain curvature. You can go through and retessellate or resurface mesh that part just at the geometry level. When you bring in a surface part, it will come in as a tessellated structure that's shown right here, but this tessellated structure that's all you have. It's dependent on how it was ever tessellated when that file was saved or exported. It will show up under your parts window as a green part, and this does make it a little bit challenging to work with. So let's kind of jump over real quick into STAR, and we'll kind of show an example of, what's the best way to handle a surface mesh file like we're looking at right there. So if we open up STAR and we can go to File, Import our surface mesh. This is going to be an STL file of that manifold we were just looking at. On importing a surface mesh, we want to set the dimensions that it was coming in at. This was originally exported as millimeters. So if we bring in the part, we kind of see it here, and it looks like a very nice, clean part. It was a CAD part that I just saved out as a STL file for this demonstration. But we click on the surface mesh button up here and we can see kind of the tessellations of how this was saved out. And what we want to do is, in order to extract the fluid volume, which is really what we would be interested in CFD, is we need to cap off these ends and then figure out some way to get that volume out that represents the inside of this manifold. Right now we're looking at one surface. We'd really like to identify and break out what these end faces are. In most CAD parts, you can always go to kind of a split by patch. That doesn't work here. It only sees a part as one complete patch. One thing we can do though is we can split by angle and just kind of force it to look at areas where there's at least a 90 degree or anything over 89 degrees and kind of split those surfaces up. So we at least got kind of a representation or a breakout of the inside walls here. The next step that we can do is go to our surface repair toolkit, and this will give us some features for dealing kind of directly with the surface geometry that we have. Over here on this right side, this is our diagnostics tool. Just to kind of bring it up real quick, you can hit manage and click on items that you would like it to identify, and then hit OK, and items will show up kind of in red, either in red, blue, or orange and green or yellow. Items in red and blue are kind of things to watch out for, because those will make it difficult or stop your process of being able to mesh. Items in yellow and orange are typically just misshapen or narrow tessellations that it's calling out. They typically won't harm you going forward. The first thing we want to do though is we do want to cap off what these ends are. So if we go over here, we've got this first feature repair toolkit we could use called Mark Feature Edges. And it's going to look for edges that are greater in this step of 31 degrees. Now we actually have some feature edges that we can go forward with. And the next tool is based on what those feature edges are. It's going to look for closed loops, and we're going to do a fill holes using selected feature edges. So now with those two clicks, we've basically have capped off the ends of our parts, and we have an internal volume that we can move forward with. From closing this here, I still want to go through and kind of break up this surface, because now it sees what we originally had as the ID surface of the manifold. It's all labeled off as one surface. Again, I can do that split by angle here and kind of split off, and now we have exposable end faces. A couple more options to do right here, or actually basically it's just one option to do. We can go to our surface prep and use our surface wrapper. This is going to be very lightly touching on surface wrapper. Surface wrapper is basically a tool that could hold its own webinar on its own. This is essentially going to be another mesh that's going to be created within STAR and help us kind of redefine what volume of interest that we have. If we open up the detail controls, you'll see that it's very similar to the way that kind of the meshing operations are set up. You provide it a base size. Based on the base size, it's going to create a mesh and create minimum surface cell sizes. We have options down here for custom controls to refine in certain areas and then look at ways to prevent contact or defeaturing with the wrapper. For now, we want to kind of set a relevant surface size. If we kind of bring up our tool and just kind of measure over here the ID, we see we've got about 35 millimeter ID, so we could set this to maybe 10 or 15 millimeters. The other item that we want to pay particular interest in is what the volume of interest is. Right now on default, it's set to largest internal. We have options for external. So if we were looking at air flowing over the surface of a body, we would select external. We could also be a little bit more refined on selecting either a seed point are an nth largest domain. But with largest internal, we can go through and execute this. And we see under here in parts, there's a new part that's been created that's called our surface wrapper, shown right here. If we bring this over into this scene, we see that we now have an idealization of the internal volume of that manifold. And from the surface wrapper, we can add this to create a region for that, define the surfaces that have been separated at the ends for our boundary conditions and our wall and inlet conditions, and move forward with the analysis. Kind of on the next example, it's going to be another manifold, but this time it's going to be a CAD geometry. And this is what our preferred workflow is. Anytime that you can start off with something in CAD, it makes things a lot easier and makes things a lot better and gives you more advantage on going forward and being able to make changes to the part, make changes to your domain, and be able to do studies to see, you know, how your analysis will be affected. So again, if we go here and we create a new simulation in STAR, this time when we open up geometry, we have this folder here called 3D CAD models. We want to right click on the 3D CAD models and hit new. And this brings up our 3D CAD domain. And as mentioned before, it's a parametric modeling tool, feature-based parametric modeling tool. You see here we've got kind of our 3 datum planes at the origin that show up. Before we import it, just to kind of show you real quick ways of using this, you go here, say we click on this, create sketch. In create sketch, we get a bunch of basic shapes that show up, either straight lines, circles, rectangulars, ellipses, a spline tool. You can always go through. So if we start with a circle, create a circle, and then from that circle, apply a radius dimension. By default, everything shows up in SI units, but everything within STAR is somewhat agnostic to units. So we could set this to 6 inches. We can also click here to expose the parameter, and now we have a radius parameter out here that's been exposed. So once we have our shape, we can then go to our shape and extrude this, and say if this ends up being a pipe or something, we have our distance here of how long we'd want that. Again, you could expose that dimension for later usage and reflection to go back to, and hit OK. And now we have our first part and our first body that shows up here. And that's basically, how you would create geometry and manipulate geometry. We'll delete these 2 operations because you can always go back. And since this is a feature-based tool, delete any operations that were not necessary. What we want to do here, though, is we want to bring in a CAD model that we already have. This is, again, a 4-port exhaust manifold that's shown right here. The body shows up under the manifold group. There are some tools in here that you could do straight defeaturing on. So if we have those holes that we were kind of knowing, or kind of seeing it's a bolt hole pattern, we don't really need it for the analysis, but just to kind of show kind of an example that you could, with that defeature command, can identify, remove small holes, small chamfers, small radii that you don't really want in your analysis. One reason why I picked this part to be an example, the first time I brought this part into STAR, I capped off the ends, extracted the flow volume. Notice I only got a flow volume for this end right here, this long L shape. Any of these 3 ports that came off didn't have a volume. And what happened, I started inspecting this a little bit more, and we'll try to grab that surface right here to show you. What ended up happening is whoever made this, they were, well, we can call this a lazy CAD designer. They just made a straight shoot through, and these parts kind of go into a wall. There's no flow that's coming out of it like you would expect. Um, this is a part where if you took it into the surface repair toolkit, it's going to show up perfectly fine. You don't have any issues. The CAD geometry is good. It's just wrong. And this is where you can use a CAD tool to make some repairs. So we can grab that interface right here, and what we want to do is kind of punch through these 3 holes so we can get this back again. We go to create sketch, this time on face. And we can kind of just grab these surfaces right here. Right click and hit project sketch, and projects those to that flat plane sketch we defined on the face. We do want to get rid of these kind of cross members so that we have kind of a straight shot to go through. And now we have a pattern of the inside walls. We hit OK to exit the sketch, and then from the sketch, right click, extrude cut. By default, it does a method of through all. We want to set this to blind and maybe just, again, set this to a 1-inch cut. We just want to get in far enough so that we kind of blast out that wall that was erroneously put there. Now we've hit that, and we've got pretty much a corrected part that we can go forward with. We can bring this back into STAR and do our other operations to get it out. But one of the things that I also recommend doing is setting up what your faces are. If we look at this part right now and the named faces, there's only one face that's identified, the entire surface of the part. We only have one edge. We want to go over here. We could click on this edge, right click to rename, and we could call this we call this our inlet edge, inlet face, and that shows up here. And again, over here on our outlet ports, we could again rename this to our outlet face. And this gives us kind of 2 edges to go forward with, or 2 faces to go forward with. On this outlet face, we do have 4 ports. To further differentiate, we can go out, and I'm just going to do this for one of these ports here, is grab the edges that kind of characterize it. Grab those 8 edges and again rename, and we could call this port 1. And that kind of differentiates that feature from the other ports on the outlet face 2. Would recommend going through and doing the other 3 of port 2, port 3, port 4, but the interest in time, we'll just leave it at that. Now we'll close out the CAD, jump back into the simulation side, and right click on our CAD model, hit new part geometry, accept the defaults, come up here and open our geometry scene, and we see we have our manifold pipe situated right here. The manifold comes in under our surfaces that are named with our curves. And what we want to do is very similar to what we did before, but using the operations under the meshing pipeline to close off the faces and extract the internal volume. So operations new fill holes is what we want to select on our input parts. We've got our manifold. On our in surfaces, we've got the inlet and outlet surfaces that are going to define the 2 end regions. And then in curves, this doesn't have to be selected, but since we do have 1 port, we select that 1 port and hit OK to execute on command. And now we've got our 4 fill holes that finish out and cap off our volume. Again, the next surface operation we want to do is extract volume operation. And again, we collect our fill holes and manifold, execute upon creation, and we've got our extracted volume here. And from here, if we go to create another empty scene just to bring this in, we've got our ID volume of the manifold pipe. And we look here in our fill holes, we've got our inlet hole, we've got our 3 outlets that were undefined, unseparated, and our part manifold. And these will all become boundaries that you would have in your region when you go through and define that. The last example that we want to get into is the Predictive Office. This is our office, or one of our offices at Applied CAX, actually for our consulting wing, predictive engineering, and also with CAE right now. I'm actually sitting right over here, and Jeremy's in this little cube over here. The story behind this model is we moved into a new building a couple years ago, and it was pretty much empty building, empty floor that we had to build out ourselves. And we didn't even have an air duct in here. We just had a hole in the wall that was situated back here. So one of the models that we ended up building early on was just trying to model the airflow within our office itself. We knew we were going to have a pipe that was going to come out, a duct that was going to come out, and maybe T right here. And then the question was, how long should we move this duct out? Where should we place the outlet registers on this T? And this was set up as a parameterized model. And there's kind of a few aspects I want to highlight when we open this model and go through it. I want to highlight how the duct length and the locations of these were parameterized. But we also did some more detailed meshing on, or detailed features on the model. So each of these overhead registers, they've got this kind of a ceiling register type thing that you see right here, where it's a circular, it's got maybe a couple baffles in it. So we have some thin film baffles that we want to be able to incorporate into this duct structure. So what this also gets into is a few key operations that we need to be able to handle. We do have two different volume domains between the duct and the surrounding office that we need to subtract, make contacts for, so that we capture the solid wall interfaces. We also want to capture the thin wall interfaces within the duct domain itself, and that's going to require us doing an imprint operation and volume extraction. So if we pop open to our base model here that we have, we can go over to the 3D CAD model and hit edit just to bring it up. And here's our 3D CAD model of our office. We've got a few parts in here. We've got our main office volume. This office volume was basically created from an initial sketch layout through a base extrusion, and then we do cuts and other extrusions and other modifications to put in walls and windows and door accesses that we have. And then we've also got our inlet duct. And with the inlet duct, we mentioned the baffles that were a part of the registers are kind of shown right here on those three components. Down here under the parameters, we can see where we have the parameters identified for the overall duct length and the position of these registers. If we go to the sketch supply of the duct, that's kind of our hole where we originally started off with, the inlet duct. I believe it's an 8-inch pipe. The duct length itself, go to edit on the distance. If we fly that out, we see that's the exposed parameter of the duct length that's driving it out. And again, on the registers, these registers were basically simple revolved surfaces that started out towards the center, also with the baffles that were created. And then we used a copy move command in order to relocate where these registers each were. So we edit this command and we can see that we've defined an axis that we want it to move, kind of an axis along this cross T diameter. And then each of these are exposed with a distance register where we're either moving positive in the positive Y direction or negative. And the thing about this, because it's all parameterized, we can always go through here at any time, even in the CAD part, kind of make a couple adjustments to this. Right here, you can either adjust any of these variables that we want and hit update CAD there were yellow triangles that showed up here that show that those are parts that needed to be updated. But with Update CAD, one click, it goes through and re-updates everything that you did with the new parameters. So we close out of the CAD part, jump into new geometry part, and we're going to bring all the geometry that we had created in CAD here. We want to add this to our current scene that we have. And we have a number of operations that are already set out. So like I mentioned before, kind of under our geometry CAD, let's get this so that we can actually see this. Oh, got to change the representation sometimes to make sure that you're looking at a baseline representation. So right now we're at a geometry representation. So first item we want to do is subtract out what that duct was from the main office volume. So we just need the two parts of our office volume and our inlet duct for that command. And we create a new operation here, or create a new part there. Input parts are the inlet duct and the office volume. Our target outlet part we want is the office volume. And we execute that, and we have our new office volume here. The next two operations are going to be an imprint and extract volume. And let me create kind of a new scene right here for that, just to kind of better show what we're trying to do on the inlet duct with all these baffles. So what we want to do is we want to be able to characterize and show that we've got this new single piece of the inlet duct. Where is it? And for some reason, it's not showing. Let's go to, there we go. Auto zoom. We've got an imprint command and extract volume command. Now, the imprint command is a very useful command. If we click open, we see the tessellations of these surfaces. We notice they're not tessellated correctly. They're overlapping each other. And what the imprint command does is basically make sure all the surfaces are aligned that you have. So we want to identify all these parts that we have here, hit OK, go to execute the imprinting, and then now we'll move on our surface representation to the imprint, and we can see that all the tessellations have now removed so that they're aligned between the duct and the baffle faces. This is really important for using, especially to make sure that when we go to the meshing operation that we have an aligned congruent mesh. If you're doing conjugate heat transfers, that's an operation that you need to make sure that you have, so you're not trying to interpolate. Next on extract volume, actually on this imprint command, I want to be able to make sure that we also have that subtract included in it so that we are imprinting on the subtract volume. Again, on the extract volume, we want to extract out what the new duct is going to be. That's going to include all the baffles within it. So again, creates a new part, extract volume, and we have our extract volume and our subtract. And we can add these to our new regions, and these will basically be the new regions that we will have. And in the new regions, we have the extract part region, which is our duct. We could rename it to our duct. And then we've got the subtract, which is the total office volume. Interfaces have been created here between these two. And if we look at these interfaces, just kind of going down, we've got our baffles that are set up, our duct that's set up, and our registered ducts that are set up. Right now, these are free flow interfaces, but we want to change these over to a baffle interface because these are solid walls, thin solid walls within our solution domain. The one wall that we do want to keep open is this interface right here where the air is flowing out of the registers into the room. And then lastly, on automated mesh, we want to go through and click on the automated mesh select the two main parts that we have for our solution and kind of be able to go off from there. And what's powerful with this now is because everything has been parameterized and defined, we can always go through and make additional changes on our parameters that are exposed up here. As you see, once we make one change, things start to pop up again. Yellow triangles show that it needs to be updated, and all of our operations here are showing that they need to be updated. But with one click, we go over here to generate mesh, it reloads in the parts, re-updates all these operations, and then starts remeshing the entire assembly. And essentially, this is kind of the goal of where we want to get to. Kind of an effective mind on putting together your geometry with a focus on, in this model and simulation studies, what's key and important, what might you be changing, what can you identify that might be a parameterizable value. You set that up within STAR, setting up your physics, setting up your meshing pipeline. You can add in other parameters within STAR to help drive the different studies, and assigning the physics, running the simulation, and getting to the post-process. From post-process, you can look at the results that you've received, make changes quite quickly, especially if it's parameterized. It's just changing a few numbers here and there and hitting the restart, and automate straight back through this entire process. If we couple this with Design Manager or HEADS, we can start looking at design optimization tools with specific goals in mind. And that is the kind of end of the presentation. I guess, Adrian, do you notice if there's any questions?
No, we don't have any questions on the queue there. No, I thought that was great. One of the things I was kind of thinking of during this process, talking about the tessellated surface geometry, is if you'd already created a mesh for an FEA, you already kind of gone through the process of simplifying and idealizing your part. Can you put that mesh over here to use for CFD as well?
Yeah, and that's, I believe, exactly what was shown in the list of importing surface parts.
Mm-hmm.
You do have the ability to kind of bring in a surface that's what you could say it's come from Nastran, or if you did it in FEMAP, you could export it as a parasolid surface, and
Yeah.
that comes in as a surface. It typically doesn't have any CAD representation to it, but yeah, you would have to use a little bit more of the surface tools to do any modifications. But you can bring that in and use tools such as the surface wrapper to go forward with.
Yeah, that's awesome. Yeah, we don't have any other questions. I don't know if anyone on the line still has anything that wasn't covered. You can punch in your questions in the little chat box, or if you think of something later today, a lot of times as these things sort of process, you think of questions after it's over. I would just say feel free to email us, and we'd be happy to help you out.
All right. Well, I want to thank everyone for their time at listening, and wish everyone a good day.